For this question, we are given the graph of what appears to be a rational function because it's got some strange behavior where it appears to be avoiding some lines in the Cartesian plane. So it looks like it might be a rational function, and we are asked to select the name of the toolkit function in the graph. Now, we do have a place where we can look up toolkit functions. Let's go to this list of toolkit functions that we have consulted in previous sections. And the reciprocal function is one that we hadn't investigated until this lesson. And as you can see, it looks very similar to the one for this problem here. Okay, so the toolkit function is the reciprocal function 1 over x, right? Then we are asked to give the domain of the function and the range of the function. There's a couple of ways we could go about that. First of all, I always like to look at the graph of the function if that is provided and just notice where there are any limitations of where the function can go as far as x values, and that will help me know what to restrict for my domain, any values of x that should not be included in the domain, and any places where the function cannot go for certain y values. So here with my image, I'm just going to draw where I can tell that there is a vertical or a horizontal asymptote or places where the function will not be allowed to go or where it just cannot exist, where it's undefined. So I see here that there is a vertical line through the y-axis, and that's a little hard to see. Let me get a better color here, something a little brighter. So right here, I notice that although the function gets very close to this line, the blue line that represents the function, it never actually touches it. And this is the y-axis, that's what we call it, but it also has an actual equation, and that is that x, whoops, I almost wrote the wrong thing, x is equal to 0 everywhere on the y-axis, okay? So that is our vertical asymptote, and that helps us to know that the domain should jump over that value for x. So I can use any other value of x and it'll be fine, but just not at 0. Another way I can tell that is notice that since my function is 1 over x, if I plug in 0 for x, I'm going to get 1 divided by 0, which would be undefined. So this does make really good sense, and we'll go ahead and put that in for our domain. Negative infinity to 0, and then union from 0 to infinity. So everything except for 0 is allowed to be plugged into this function, and when it's plugged into this function, we'll get a value that actually exists, okay, for y. All right, now we can talk about the range. So again, looking at my image, I want to notice that I have another line that the function appears to never be making contact with, and that is a horizontal line, so it should have the equation y equals a number, because everywhere on that horizontal line, y will have the same value always, and that is the x-axis where we have not moved up or down, so that is where y is always equal to 0. So the equation of the x-axis is actually y equals 0, and that would be a horizontal asymptote. But that will help us in defining our range, because as we can see, the function goes very high for y values here, and then it goes very low into the negative for y values and continues on in that direction. And just in case you're not sure, even though it doesn't show it, you really should see arrows on the ends of our function to indicate that the function is continuing in that direction. So the y values continue upward without bound, they continue downward into the negatives without bound, but there is a weird behavior here where the function veers off and never touches the y equals 0. So y can never be equal to 0. So our range will be pretty much the same thing as the domain. We just have one value of y where the function does not exist.